Okay, so good morning, everyone. Welcome to another session of the Research Seminar Committee. Today we welcome the Nobel Prize of Physics, Professor Duncan Haldane. Professor Haldane began his career in Europe, working at the Institute Law Langevin before moving to the United States, where he held academic positions at the University of Southern California and the University of California, San Diego. Since 1990, he has been a professor at Princeton University, where he holds distinguished titles, including the Sherman Fairchild Professor of Physics. He is widely recognized for groundbreaking theories such as Luttinger liquids, one-dimensional spin chains, and key advances in understanding the fractional quantum Hall effect. His work has profoundly shaped modern quantum physics, introducing new ways to describe complex quantum states, including geometric approaches to quantum phenomena. In 2016, Haldane was awarded the Nobel Prize in Physics alongside David J. Thulles and Michael Kosterlitz for their theoretical discoveries of topological phase transitions and topological phases of matter. Their work applied concepts from topology, a branch of mathematics that studies properties that change only in discrete steps to explain unexpected physical phenomena. So you can continue, Professor Haldane.
Well, thank you. I expect that most of the time you hear talks about the very large scale aspect of things in the universe. I mainly work on very small scale, but at least here there is experiments on quantum communication, which kind of brings us together with my interest in quantum mechanics. Okay, so I'll tell you a little bit about some of the things that we're doing. So, of course, the modern laws of quantum mechanics are now 100 years old, and they're correct so far. But just because we know the laws doesn't mean we know everything that you can do. These laws allow to happen, and quantum mechanics has been a lot of, at least in the condensed matter regime, has been full of surprises about some of the strange things that quantum mechanics allows to happen, and that we're trying to find technological applications for. So around about 1980 in my field, the condensed matter physicists thought they knew basically everything. They had big theories of magnetism and phase transitions, and they thought it was just a question of cleaning up some of the details. And of course, whenever a field starts to think that way, it's heading for it's too proud of itself, and it's heading for some surprises. And indeed, around about 1980, two of what we now call topological states of matter were found because they exhibited kind of strange properties which didn't fit in with the way people understood the physics of matter at that time. And it turns out that these things all involve, in some sense or other, quantum entanglement. And interestingly, both these two discoveries, mine, which is more obscure work on magnetism, and von Klitzing's work on the quantum Hall effect, which has led to a new system of units to replace the lump of platinum, which was the kilogram in the French in a safe in Paris. They both happened almost at the same time, within a year of each other, almost at the same place, but of course completely. At the time, there was no obvious connection between these two things. But in the meantime, it's emerged what they really represent, and there's been lots more kinds of examples of topological quantum matter that have emerged, and there's a huge amount of excitement in this area, lots of experiments and things going on to study this stuff. So what is topological matter? It actually differs for an ordinary matter in some sense, because it's got some intrinsic properties which can be viewed as something to do with their internal entanglement that can be described by whole numbers. So usually you're doing measurements, very precise measurements of the fine structure constant or something to 12 significant figures, very accurate things, and you have to do very fine things. Here, the amazing thing was there's some kinds of matter where the numbers involved were whole numbers, integers. And states of matter which are characterized by different whole numbers can't smoothly change into each other. So something always interesting happens at the boundary between different regions where their classification is a different whole number. So if 0 is a kind of trivial number or means that there's nothing old regular matter, then if there's a region which is classified with -2, there has to be a boundary because you can't go continuously from 0 to 2. And interesting things generally happen at the boundary. So soon after these discoveries, a kind of a framework for starting to think about them emerged when Michael Berry discovered what's called the Berry phase, importance of the Berry phase in adiabatic quantum mechanics. It's not that it wasn't there to be seen earlier, but just the importance of the fact if I take a quantum system around the closed path and bring it back to where it started from, the state of the quantum, and compare it to a similar system which I didn't take around that closed path, there's an interference phase between the two, and this is non-trivial. So this took a long time to be realized, but its simplest example is if I take a spin which is pointing in some direction, and I make it go, and I adiabatically move a magnetic field that's causing it to point along the magnetic field, and I slowly drag it around and to where it was before, you get a phase which depends on the solid angle subtended by the path on the sphere, the celestial sphere around it. But the solid angle is only defined modulo 4 pi. So the number which multiplies that has to be an integer s, which s is or 2s has to be an integer. So s times 4 pi is equal to 2 pi and is equivalent to 1 for a phase going around. So this is a kind of the archetypal Berry phase, but it applies to also all quantum systems. If you move them around a closed path, they pick up. If the time reversal is broken, so otherwise, if time reversal is not broken, if I move them around the path and move them around all I can get is a plus or minus 1 phase. But the interesting cases are when the system has broken time reversal symmetry, like a spin, which is called an angular momentum pointing in some direction. Okay, so adiabatic quantum mechanics considers a system where the Hamiltonian has a slow variable which we can pretend is a classical variable that someone is controlling. So if you're controlling this quantum Hamiltonian and x is a variable that you control, like a video game, you move it around, and you move it around slowly enough so there's no transitions between the eigenstates of this Hamiltonian, then I describe this by adiabatic quantum mechanics, and this fulfills the condition of I can compute the phase for going around the loop. So there's various interesting stuff. There's also a quantum distance. There's a quantum geometry associated with the Berry phase. The Berry phase is the imaginary part of a more general structure, which includes a distance measure between quantum states. And interestingly, people have been struck by the similarity between Berry phases and electromagnetism. And that's not an accident, because the adiabatic phase in the Bohm-Aharonov phase, for example, is a special case of the more general Berry phase. Okay, we'll come back to that. So there's a kind of feature, the Berry, which is a bit like the vector potential in electromagnetism, right? The Bohm-Aharonov phase says that if I take a particle around the closed loop, a charged particle, it picks up a phase of the integral of the vector potential around that loop, which is equivalent to the magnetic flux going through that loop. And in adiabatic quantum mechanics, there is a vector the analog of a vector potential. It doesn't have to be just in 3 dimensions, like in 3-dimensional space. It can be in whatever the parameter space of X is. And the example is to actually see you've got a stick with a little quantum bound state, a little quantum well on the end of the stick, and I have an electron sitting in that bound state. And it's a bit like moving a cup of coffee around if you're carrying a cup of coffee, if I move it too fast, it'll slosh and spill over the cup. If I do it very slowly, so as I move it, I'm not disturbing the level of coffee in the cup. I do it adiabatically. If I move this around the electron and there's external electromagnetic fields, the electron will at first feel the electrostatic potential, which controls its energy as it moves, the energy of the electron relative to the well as it moves around. And because it's got a finite speed, it's going to have a Lorentz force, a V cross B force on it, a force which doesn't change its energy, a velocity dependent force. And these two things are actually present in general. So this reduction of electromagnetism, in particular electromagnetism of a particle which is not free to move by itself, but is controlled by me as the classical agent, gives rise to what's the precise analogy of the electromagnetic force. The quantum Lorentz force is minus the gradient of the instantaneous energy of the system at point X, which is like the electric field gradient, the gradient of the potential. And then the second term is h bar times this Berry curvature, which is the analog of the magnetic field, expressed as a Faraday tensor. So it's a very interesting feature and this underlies most of the kind of work on topological states in some way or another. And they have all the kind of stuff like gauge dependence of, the paradox of quantum electromagnetism is that things depend on the vector potential, which depends on gauge rather than the magnetic field strength itself. But if you go around closed paths, the gauge choice doesn't matter. Okay, so this is a kind of interesting underlying kind of quantum geometry, and the phases give rise to topology in quantum mechanics. Okay, so there's a lot of work now on earlier work focused on things like the Berry curvature. Now there's quite a lot of work on the implications of the quantum metric in various systems. Okay, so which defines a speed in Hilbert space and things. Let me move on. Okay, so before the Berry phase depended on the spin S, and it required that the spin S of a spin has to be integer or half integer, right? The usual way you learn that is from an algebraic viewpoint. You've got a ladder of states between minus S and plus S, and it has to terminate at both sides. And from that from the algebra of the raising and lowering operators, you determine the quantization of spin. But this is a different way to understand the quantization of spin, a topological way, which is actually goes back to Dirac's magnetic monopole in the 1930s, which was also where the flux emerging from a putative monopole has to be quantized in units of the flux quantum times an integer. Okay, so my own work on this back in 1980 was at that time it was known that the spin 1/2 one-dimensional antiferromagnetic chain, which was then a kind of toy model, was gapless, because Hans Bethe, who went on to tell us, how the sun works, initially as a postdoc, he worked on this model system and stumbled. He made a happy accident because he accidentally discovered an exact solution to this problem, and he solved it exactly. But it's taken about 60 years to understand why his solution works. He didn't understand why it worked because his paper says, I'll generalize this to 2 and 3 dimensions in my next paper, which of course never happened. But so most of these kind of unexpected things, these kind of interesting discoveries are things quite unexpected to the people who discover them, right? I mean, it was a kind of judicial guess. So and the properties that of Bether's solution, which was only gave you energies and didn't give you any method for calculating matrix elements or physical properties, just energies. They looked extremely similar to what magnetism would predict from semi-classical spin wave theory. So it fooled the magnetism community into thinking that the spin entered not as a number 2s, which is an integer, but as a number 1 over s, like a real number, which varies from 1 over s goes to infinity, 1 over s goes to 0. It's kind of like Planck's constant. They thought it was like Planck's constant that would vary continuously between, I guess, 2 and 0, or 2 and 1 over s would vary between 2 and 0, and the properties of the magnetic properties would be just continuously variable along that path. And so, people were fooled by a mathematical solution they didn't understand and interpreted in terms of semi-classical pictures. Okay. Well, around about 1981, I discovered that this spin 1 chain rather than spin half chain of quantum spins actually had a state which was completely different from the predictions of magnetic theory. In magnetism, before one assumed that the spins were like little magnets. Now you could order them in different ways to make different kinds of structure. This is an antiferromagnetic structure where the spins are alternately pointing up or down. And you just build this magnetic structure by bringing these little atoms together and stacking them in a certain way, but there's no fundamental quantum entanglement between the atoms. And it turned out that the state I discovered has a representation like this, where the spin 1s break into 2 spin halves, essentially, and half of it joins with one of the spin halves of each neighbor. So you get the thing like valence bonds connecting the things in the interior of this chain, and you get a leftover, very tellingly, you get a leftover spin 1/2 at either end of the chain. And this is a typical thing that happens in these topological systems. You have fractionalization, and here you have something unexpected at the end of the system, the boundary between this state and the normal state on the other side, a strange thing at the edge, half of a spin. Okay. And if I get to the end of this talk, there'll be even stranger things along the same line of this. Okay. Okay, so this actually was very controversial. The people in the magnetism community really reacted rather badly towards these predictions and kind of initially said they were complete nonsense and prevented me publishing and all kinds of stuff like that. But controversy in science is really good for advances. A lot of people got interested in the controversy, and it actually led to the development of a lot of interesting techniques, both experimental and theoretical, which have turned out to be extremely useful for investigating all kinds of other problems in the field later. In particular, the material scientists are the heroes of all this stuff because they're able to build things. This was a toy model when it originated, a one-dimensional chain of spins as a toy model for a three-dimensional antiferromagnet. But now we've recognized these low-dimensional structures are actually somewhat more interesting than the three-dimensional ones because the quantum effects are much larger in them. And the chemists managed to build a chain of a one-dimensional chain of spin 1 nickel atoms in some organic backbone here. Anyway, so the thing from a field theory perspective, although the original way I discovered it didn't involve the topology, it turned out the difference between integer and half integer spin was something called a topological term in the Lagrangian, a so-called theta term. The theta term actually has an interesting history, and it's now believed one of the theories of dark matter, which probably you guys are interested in, is Wilczek's axion approach, which is basically a theta term in the I guess the weak interaction Lagrangian, which allows, and the axions are postulated to be fluctuations of this angle theta, which is very small because there's only a small breaking of PT symmetry. Okay, so this term is present And yeah. So in the spin chain of the simple kind, theta could either had to be to avoid the antiferromagnet wasn't actually breaking time reversal symmetry because there were equal numbers of up and downs in it. And this requires theta to take the value either 0 or 2 pi, 0 or pi modulo 2 pi, and it turned out that integer spin was 0 and half integer spin was the case. So it turned out that what I discovered was actually the canonical behavior, and the properties of the model solved by beta were the strange behavior where, because this angle was pi, there was an interference effect due to the fact that a spin half, when it goes around a complete circle, 2 pi picks up a -1 phase. Okay. So anyway, but there's an example to show you that, often we have a lot of preconceived notions and which sound very convincing, like the spin wave theory of these things. And maybe there's something we think is evidence for these, which makes us even more sure of our conviction that something is right. But very occasionally, the evidence is actually being misinterpreted and things are not the way we think, So there's the problem of if there's something appears to corroborate what you believe, you of course accept it. And sometimes you get fooled. Okay. So the picture of this particular state is a group. Hands usually come in pairs, unless someone has had an accident or something. There's kind of locally, there's 2 free hands to move. If an organism made out of a chain of people holding hands occurs, then there's 1 free hand at one end of the chain. We've had fractionalization of hand pairs into independent hands at either end of the chain, which is the thing. Okay, so the quantum Hall fluids are perhaps the clearest examples of topological states, actually. So they're originally found in large magnetic fields where electrons go around in little circular orbits, and in the quantum Hall effect, they're confined to a 2-dimensional plane, usually a crystal plane in a semiconductor where someone has built a quantum well or a sheet of graphene. And so there's periodic motion in the plane, but they're not spiraling along the magnetic field lines like the electrons released by the sun's energy hitting the atmosphere does, right? So the electrons have periodic motion, and von Klissing discovered by measuring a device that in a certain range of magnetic fields, he found this conductance, the Hall conductance, which is the voltage transverse to a flowing current, or the relation between voltage and current, which is transverse to the current. He found it was a whole number times fundamental constants E²/h. And you see this plateau here. And for initially, people wondered, how can this be? This was a complete surprise. And I'll come to that in a second, the surprise aspect. People wondered, are there any relativistic corrections to this? No, in fact, when you're using SI units as opposed to the Gaussian units that my colleagues seem to be my older colleagues at least seem to be totally wedded to in the States, there's no speed of light, there's no c in this formula. And this has got absolutely nothing to do with relativity, right? This is just quantization of charge and Planck's constant. And anyway, wherever there's a whole number, it turns out that there's an exponential fall off of depending on the size of the system, and provided the system is large on a microscopic scale, the corrections are exponentially tiny. So it's nothing like 1 over like velocity dependent corrections to classical physics in relativity. Okay, so now we got rid of the kilogram, and every country can have its own kilogram made out of a quantum measurement, the Kibble balance. Okay. So actually, these discoveries, actually, like mine, was also a surprise because I came at it from a completely different direction from the magnetism community. Von Klissing also had the luck to do his measurement. In fact, the same experiment von Klissing did had been done essentially the same earlier, but nothing was seen. Why not? It's a question of luck. There was a Japanese experiment where the experiment is to put an object with a constant current moving through it in a magnetic field and measuring the whole voltage transverse to the current in a kind of thing, something called a Hall bar, which looks a shape a bit like this. So you have a current flowing that way and you measure the voltage transverse. The Japanese protocol was to take a system, go to a place with a constant magnetic field. The magnetic field was turned on and stable. Then they took their sample, put it inside, turned on the current. Now, each time you turn on the current, you'll never get exactly the same current flowing through the system. So the voltage will never be exactly the same. It'll be approximately the same, but you'll never reproduce exactly the same current on any two shots of this experiment. They saw nothing of interest. And of course, they were kicking themselves a few years later when von Klitzing did it the other way around. He prepared the sample with a constant current flowing through it, put it inside the magnetic system and turned on the magnetic field. And as I showed you in that picture, this number is stable in a finite range of magnetic fields. So while you'll never get exactly the same magnetic field each time you switch it on, there's always going to be some differences. It doesn't matter. The crucial thing was that the current was exactly the same in each run of his experiment. And he saw his voltmeter producing a voltage with some significant decimal plus 4 or 5 significant places after the decimal. So of course, first he thought his voltmeter must be screwed up, right? But then he quickly found, no, this was a real effect. And then history immediately recognized that something completely unexpected had happened. And of course, that was a very interesting thing. And of course, in this case, it was such an obviously important thing in metrology and stuff. It actually got a Nobel Prize very quickly. Okay, so the topological nature of the quantum Hall effect took quite a bit of time to become clear. People really hadn't thought about topology at that point. And I hadn't found out any topological aspect to what I found early on either at that point. But one thing that was pointed in the quantum Hall effect, you have particles in a two-dimensional plane with a magnetic field going through it. And in a magnetic field, the charged particle goes around in little loops, and the periodic motion is quantized. So in the picture of this thing in the interior, I've got these little circular orbits of a fixed size now because of quantum mechanics. And if there's no electric field inside the bulk, the center of the orbit doesn't move. If I apply an electric field, the center of the orbit will move at right angles to the electric field in the plane. But at the edge of the sample, there is a potential which is not flat, and it goes up. And in fact, as you get to the edge of the sample, if you get to within an orbital radius, the center is within an orbital radius of the edge. Instead of completing the orbit, it will go round and hit the edge and go round. And if they're all going around in this picture clockwise in the bulk, the edge orbit will be anti-clockwise. They'll skip around the edge. And this is something really strange. You've got transport at the edge, but going in it's a one-way street only, okay? And this should have been, of course, no one was thinking topology initially, but that's a typical feature of a topological system, something really strange happening at the edge of the system, okay? And initially it was thought that you needed dirt to get this effect. And after people scratching their heads for a few years, they convinced themselves localization of quantum wave functions due to disorder in the bulk had to be underlying this. But in fact, you actually don't need dirt in this thing. You can have a perfectly clean interior, provided you've got a finite ratio of the area of the inside to the perimeter of the outside. Or the ratio is the perimeter on the outside times the radius of the orbit, which is called the magnetic length. Has to have a finite ratio to the area in the inside. Then you actually have a finite range of magnetic field in which this thing happens. It's because at the edge of the system, the electron states go up in energy because the orbits are not being obstructed by the edge. And as long as the Fermi level, the highest occupied level at low temperatures, is in this range between the lowest of the periodic motions, the lowest Landau level, and the second one where you have a gap in an energy gap in the middle, then you're pinned and you'll have this quantum effect here. So the edge states fall off with this exponential behavior. In fact, it's in this toy model, it's actually a Gaussian behavior. It's even faster than exponential. So provided the length of the system is large compared to the exponential decay fall off, then we have this stable range in which you get a quantum Hall effect, and you don't need to fine tune the magnetic field. So another remarkable thing about the quantum Hall effect is if I change the magnetic flux through the system, the number of orbitals in the bulk changes. Because in a Landau level, there's one orbital for every quantum of magnetic flux through the system. And when I've got these particles going one way around the edge, they're obeying a periodic boundary condition, and the Baumol-Hausdorff phase controls what phase they have by going. By going once around the system, the phase is controlled by the flux through the system. As I gradually change the flux, the quantization of these levels changes, and they're either pushed into the bulk or pulled out of the bulk through the edge like a kind of plumbing pipeline. So the remarkable thing is then that the energy, the density of electrons in the middle changes continuously with magnetic flux through the system. Now, superficially, that's a violation of gauge invariance, right? Which tells you that charges can, if you've got a system with a gap and you change the magnetic flux through it, there's no way that the charge density should change, because where those electrons coming from is only because of the edge states, which allows this strange behavior. And we actually see something else strange here is that since the density of orbitals can change, the density of orbitals has become completely detached from the underlying lattice structure of the condensed matter, where there's usually one orbital per unit cell or something like that. So the orbital is actually free to move in the background without being affected by any crystalline structure in the underlying material, which is important. So this is actually one of the most remarkable parts of the Hall effect. Not that there's this quantized relation between current in the y direction and electric field in the x direction. There's a similar thing called the Strader relation, which is a quantized relation between electron density, charge density, and magnetic flux. Okay, and this is a very strange property of quantum Hall systems. And the Strader relation, initially all the work was done on transport measurements, measuring the current, Hall current is when you had a Hall voltage, when you had a current flowing, a transport measurement. But now this is actually happening. I'll come to this point. We've actually managed to find systems where you don't need a magnetic field. And it's in graphene, in particular in graphene sheets or bilayers of graphene. And there you can kind of change the electron density in this two-dimensional system by varying a gate voltage, moving it up and down and calibrate it that. And this is a measurement that shows where the yellow shows you where you get incompressible systems, where there's an energy gap in the bulk. And you can see as a function, there's a finite straight lines with a finite slope which measure where you get this quantum state as a function of electron density this way and magnetic flux this way. So a straight line would be a boring case. When these slanted lines with a particular slope are the interesting cases. Now, this is actually showing you fractional cases. This strong yellow one is an integer one, the original one seen by von Klitzing, but now we actually have these fractional things, which I'm going to come to. Okay, so the Strader formula is actually telling us this very strange thing that the orbitals, the electron orbitals, which holds the electrons, they're flowing inwards or outwards from the edges of the system as I change the magnetic field from these edge states. Very strange. And it turns out that, as I say, we can if I apply an electric field to the system, if there's a magnetic field in a Landau level, the electrons will move at right angles to the electric field in a dissipationless fashion, so they conserve their energy by moving along the electric potential lines, and they move at this drift velocity E over B, the standard drift velocity of plasmas and things. But now we have these kind of versions of this which don't require a magnetic field, and they have a topological number which is related to Berry's phase called the Chern index. And these things also show the feature that you apply an electric field and the current moves at right angles to the electric field, proportional to the electric field, but instead of the magnetic field, it's got stuff, a topological number, the Chern number, and something like the area of the unit cell divided by the magnetic flux quantum. So it's kind of a rather general picture, which is rather interesting. So a bit later, although my initial work was on magnetic chains, I actually worked on this problem after Laughlin discovered the fractional case. And in fact, I found out that you could actually have the quantum Hall effect without a magnetic field in a structure which was a toy model at the time, which looks very much like today's graphene. The picture of graphene is a hexagonal lattice of carbon atoms. This model generalizes a bit to be something like boron nitride, where you've got a boron and two different atoms here. But I introduced a kind of complex hopping matrix elements, which are time reversal broken, to give you a kind of handedness for hopping around the interior of these hexagons. And that remarkably gave rise to a quantum Hall effect. So the crucial thing was that time reversal had to be broken. You don't need a magnetic field for that. You can get it just from ferromagnetism. Okay. Time reversal broken because the edge states go in one particular way, one way or the other way, depending on how the time reversal is broken. If I take a movie of it and show it backwards, they will be going the other way. So the fact you've got this one-way transporter on the edges indicates that this particular topological state requires time reversal breaking. There are more general ones, which are actually simple generalizations of this model, where you put spin in and spin orbit coupling, and then you can get edge states which go both ways. Okay, so how does this happen? This is actually a model, starts with a model of graphene. Graphene is just this carbon structure like so. And if I make an edge to graphene, a so-called zigzag edge here, you'll find graphene has these places where the conduction and valence band touch at things called, like, we call them Dirac points. And there's an edge state which connects the two Dirac points in part of the edge Brillouin zone as I go along the edge. So I've got this structure in graphene in the zigzag edge. I can either break the symmetry which causes the bands to touch by either breaking spatial inversion or time reversal symmetry. If I break spatial inversion symmetry, I just get a boring semiconductor out of the graphene. It's the boron nitride structure. And then the edge states are either attached to the valence band or the conduction band. Okay. But if I break it with this time reversal thing I introduced, then interestingly, on one of the Dirac, a gap again opens, but in this case, one end of the edge state is connected to the conduction band, the other to the valence band, and necessarily get these one-way edge. The slope tells you the velocity along the edge. These one-way edge states which have to connect valence and conduction band and allow states to flow between the conduction and the valence band through the edge. Okay. So this was actually predicted in 1988, and it took until 2013 before it was actually experimentally verified in China. Now this also gave rise to what are called topological insulators, because two copies of this model turn out to be stable in 2D and gave rise and were able to be generalized to three-dimensional structures, which this quantum Hall effect is intrinsically two-dimensional. And it's actually had applications in photonics too. So this general principle that you get these one-way edge states has been very useful. And there's a whole lot of, in photonics, there's no quantum Hall effect as such, but there are these one-way edge states. And there's a lot of work in topological photonics, which grew out of all this now. Okay. So the integer Hall effect was soon followed by a bigger puzzle. So as I said, after a few years, people had got over their surprise about the integer Hall effect and come up with an explanation involving dirt rather than topology and localized states, and convinced themselves that the quantum Hall effect, always you had to get a the only value for the conductance you could get was an integer times e squared over h. However, these guys, Stormer and Sui at Bell Labs, using this device made by Art Gossard, who didn't get the Nobel Prize because you can't give it to more than 3 people, found a measurement where you got 1/3 E squared over H. So immediately people thought they solved the problem. We've got a theorem, exact theorem, that shows it's always an integer times E squared over H. Something else was found. And Dan Sui actually, immediately when he saw this thing, he realized that 1/3 E squared over H, if the number always had to be an integer, had to be 3 times E by 3 squared over H. So you had to have fractional charge in the system. And indeed, he was correct. If the elementary charge in the system is E, then you can only get an integer times E squared over H. But if it's E star, I'll get an integer times E star over H. And 1/3 means 3 times E by 3 squared over H, it turns out. And the general form is P over Q. And indeed, this was really thing. So this is an example of the stability of topology. This device wouldn't get you a job in the Intel fab in producing high quality computer chips, but the soldering and the stuff is fine enough because the topological thing is robust against topology. Can't change continuously, so you have to do significant changes to something with topological structure to destroy the topological structure. Okay, I was going to say that this guy, Rob Laughlin, if I don't have this number m in here, this is a standard Slater determinant, a typical wave function people would use for electron systems which have to be anti-symmetric in the exchange of the electrons. He actually did put a 3-body system on a computer for other reasons and stumbled across this wave function as a particularly low energy state of the 3 electrons with an m equals 3 in here. And we'll come back to what this means. In the Slater determinant, every particle occupies 1 orbital, and that's how way you think of filling orbitals up 1 electron at a time. In some way, if this number is 3, which it is for the 1/3 case, you can actually think of this as every electron is occupying 3 orbitals. Okay, so it's not the Pauli principle that's stabilizing it. It's actually electron repulsion. We'll come back to that. Okay, so the foundation of our understanding of the fractional Hall effect is this Laughlin wave function, which has a very appealingly simple form in the plane. And it's confirmed by exact diagonalization of small numbers of particles, but big enough to be sure that this was actually a correct explanation of the 1/3 fractional Hall effect. And it's an interesting wave function because it doesn't fit into the standard kind of methodology of diagrammatic perturbation theory and quantum field theory. It's complete, so it still remained mathematically intractable because all the standard methods of many body physics, quantum physics, couldn't be used on this because they're all based on referring something back to a non-interacting particle system or non-interacting harmonic oscillators, and then perturbing about that. This is completely different when it can't go continuously to a non-interacting system, and it's still an interesting problem. Okay. So let's see, where am I? So Loftus state has really been the fundamental for understanding this thing, and a picture of flux attachment is in there. So let me quickly move on. So it turned out that this toy model I introduced, you can play around with the parameters and make one of this graphene-like model has 2 bands, and I can make one of the bands very flat. And the Landau level is a flat level, so there's no kinetic energy in the Landau level. So the interactions dominate. If the level is slightly broad, but is still less broad than the strength of the interactions, you get the same effect. And it turns out that you can get a fractional Hall effect in this toy model if I choose its parameters to make the lower one of the 2 bands, the lower band, essentially flat. And this is showing you that if I keep in this energy gap between the levels here, as I vary the magnetic field between -1 flux quantum per unit cell and +1, I can go continuously from having the 2 bands of this 2-band model completely empty to be completely filled when you stay in the gap. And you see that if in this gap, the electron density tracks the magnetic flux density. And now this has now become experimental. Initially it was just a numerical toy model calculations. Now we're taking graphene sheets and slightly twisting them, or putting graphene on boron nitride, and get these moire patterns like you see in net curtains, where the interference between the two patterns gives you a structure much larger than the atomic scale and can give you very flat bands. And there's a huge amount of work going on these things right now. And one of the issues I'm trying to resolve is most of our understanding of the quantum Hall effect, the fractional Hall effect, is based on Landau levels. And the question is with a magnetic field, and the question is to translate that. Now we see the same phenomena happening in periodic systems with no magnetic field, just magnetism. And the question is how to understand that. And I guess I'm probably not going to have much time on this thing, but a crucial thing in the Landau levels is we get this quantum geometry emerging. The electrons in the Landau level, electrons are going around in an orbit around the so-called guiding center of the Landau orbit. And while the electron coordinates little r kind of commute with x and y coordinates commute with each other, they split up into the guiding center is the difference between the Landau, is the position of the electron minus the Landau radius. And individually, these two terms, which add up to the electron thing, have a non-commutative algebra. It's a Heisenberg algebra. So you actually have interesting quantum geometry with non-commuting coordinates showing up. And then one question is how that happens in the lattice. And a special feature in this Landau levels, which is from these non-commuting coordinates, I can find a basis of states, of quantum states. I can choose a center arbitrarily, and I can produce they can initially be a circular state, but actually I can choose an arbitrary ellipsoidal shape to make a basis of states. And I get a kind of onion ring pattern of states with one magnetic flux quantum of area in between each of these circles or ellipses. And the Loftin state has the interesting property that if I choose a particular one of those bases, actually each Loftin state has a parameter which corresponds to the choice of the ellipticity. If the central orbital is filled, the next two orbitals are empty. And this actually gives rise to this picture. I'll say that you can say that in this case, instead of electrons filling one orbital, electron is actually filling three orbitals. It does that because of the short distance Coulomb repulsion between the electrons. And by each electron surrounding itself with not just its own orbital, but two extra orbitals to form a group of three orbitals, it's kind of shielding itself. It's keeping all the other electrons further away from it to lower its energy. So putting that electron cements the group of three orbitals together. And this is only possible because the orbitals have been freed from the lattice. In a usual band insulator, the orbitals are kind of glued down to the underlying lattice, and the electrons tunnel between fixed orbitals. These orbitals are free to move, so they've been liberated from the lattice, so they can travel with the electron. So the electron, like a tortoise carrying its shell on the back, carries its extra orbitals as it moves because they're no longer attached to the lattice, which is a really strange thing. And the 1/3 charge I mentioned was this group of three orbitals with an electron in it is cemented together because of the energy the electron gains by grouping them together. When I pull the electron out of this group, the orbitals are free to split and are no longer held together. There's no energy cost. In fact, there's a negative energy cost of having them together. So they lower their Coulomb energy of the system by drifting apart. And so if you remove one electron, you removed one charge from the system. So that means 1/3 of an electron for each orbital, and that's exactly where Dan Sui's 1/3 of an electron came from. These basic objects that float around the empty orbitals carry a missing charge of -1/3 of an electron. And all kinds of weird stuff follows from that. These objects not only carry a fractional charge, they have a non-trivial phase when they go around each other. They're neither fermions nor bosons. It took a long time to experimentally prove all this stuff. The charge was easier. If you're in a hut with a tin roof on top when it's raining, like it probably rains a lot here, and you'll hear if it's raining with very large rain droplets, you'll hear a different sound from lots of little droplets falling on. So listening to the noise of the raindrops falling on your tin roof, you can determine whether it's big drops or little drops. And exactly that noise measurements were established quite quickly that the charge carriers in the system was indeed a 1/3 charge for this particular state. And it took a bit longer to show the fact you've got non-trivial phases when they move around each other, but that was achieved a few years ago in 2020. And so these things are kind of pretty interesting, but it gets even more interesting, although we don't have a proper experimental stuff yet. So there's a more interesting case of quantum Hall systems called non-abelian quantum Hall states, fractional quantum Hall states. So Laughlin had his state. These guys, Moore and Reed, came up with a kind of a variation of the Laughlin state, a slightly different state, using some kind of connections to conformal field theory to inspire them for choosing a wave function. But this has this non-abelian feature. And this fellow, actually, Kitaev, pointed out the non-abelian states have a property that you can hide quantum information from the environment in it, and then suggested these would be, at least on paper, a solution to the problem of loss of information by decoherence in quantum information processing. This picture, the information is moved by braiding things around. And the interesting case is that this is believed to occur at 1/2 of a filling of a Landau level. So the 1/3, the 3 had to be an odd number for the Laughlin state. So you shouldn't get a quantum Hall state at 1/2. But it turns out 1/2 is really 2 electrons in 4 orbitals, which is allowed by Fermi statistics. And so there, the elementary excitation should be 1/4 of an electron, not 1/2 of an electron. And so you can easily make a local object which is like an orbital that can either contain an electron or not, a local thing which has 2 versions, a fermionic or a bosonic version with charge 1/2. But it turns out this thing can be pulled apart into 2 half objects which carry charge 1/4 each, but which can't be created locally. And these are now called Majorana zero modes. And this is a most amazing thing. This is actually fractionalizing an electron orbital into 2 half orbitals, which is a much more crazy thing than fractionalizing a spin 1 into 2 spin halves, right? And so I start with this object and I pull it apart. Let me go back to that slide again. So I took this object which has charge, I guess, -1/2. So I had an orbital which either could be empty or filled, or this one is actually an empty orbital. So it's charged -1/2, and this is 3 empty orbitals with an electron in the middle, which is also charged -1/2, because each empty orbital carries charge -1/2 at half filling of the Landau level. So I've got 2 versions of the charge, one -1/2 object, one which is a boson and one which is a fermion. And when I pull these things apart into 2 halves, I can't tell whether I pulled the fermion or the boson apart. So the information about whether it's a fermion or boson is hidden in the entanglement string which connects these 2 charge 1/4 objects. And this is where the information gets hidden. So I have these objects which I can think of. I've got some kind of history. Here is a pair of charge 1/4 objects which was pulled apart. And there's some kind of history in the background medium of how they were made in entanglement strings. But as I start to move these things around and braid them around each other, they mix up their entanglement patterns. And that's the quantum information is stored in whether this thing whether this orbital that was pulled apart was filled or empty. Okay. And this actually says that if I've got 4 of these objects, I have one qubit. Okay. And here's a picture of the single qubit in this thing. I've got these 4 charge 1/4 objects. They actually like little internal edges. If there's an external edge which is going around with flow that way, they actually have counter propagating flow around the edges of these little objects. So this pair got pulled apart from a pair here, and here's an almost identical state, which to outside viewers looks identical because all you see is the position of the charge of quarter objects, but the history is encoded in the entanglement patterns in between. So this particular one represents the qubit pointing upwards, and in this particular case, the qubit has its spin pointing, its nominal spin pointing in the equatorial plane of the Bloch sphere, and the information is hidden in these patterns. And so this is, let's see if I go back to that. Yeah, so when we manipulate the information by braiding these things around each other, and there's actually ways to do it without moving anything. I'll come to the end of in a few minutes. So so this information is hidden in the pattern. That means if a cosmic ray goes through this thing, it's got an exponentially small chance of killing the information, right? The cosmic ray might go through a point here and zap it, but the information is spread out here. So the chance of the information being lost by a cosmic ray going through is the ratio of the area hit by the cosmic ray to the area which is where the information is stored. So this case, the information is protected while these objects are well separated. The read in and read out phase is where you have to bring these objects together to find out whether they're empty or filled is the danger part. But I can, in principle, carry out the quantum manipulations arbitrarily many times on paper at least. So what's missing in this thing? These topologies, actually, there's always an exponential decay length. These objects do have a finite size where things fall off. The Majorana zero modes fall off in a certain way, and these things have to be well separated compared to this exponential fall off length for the topology to fully protect them. There's actually a picture of some simulation of these things, I guess on a sphere or something like that, but these are actually two different states of the 4 qubits, and if they're finite distance apart, you can see there's very tiny little ripple patterns, which are interference fringes, which can allow me to tell you which direction the qubit is pointing in. But as they become further away from each other, the size of these ripple patterns becomes exponentially small and becomes basically invisible as you pull these things apart. Okay, so this thing comes from Majorana. Majorana was a kind of very interesting guy. He came up with, he showed that the Dirac fermion could be split into real and imaginary parts called Majorana fermions. He was a bit strange. Fermi tried to get him to write his results up and he couldn't get him to do it. So Fermi wrote the paper for him. And a bit later, he went on a boat ride somewhere and never got off at the other end. So we never know if he jumped off the boat or he disappeared to some mysterious country. But Majorana found this stuff, and the Majorana zero modes are not exactly a half of a Majorana fermion. The box itself, which is empty or filled, is the Majorana fermion, or the state of it. But by pulling the Majorana zero mode is something even stranger. It's like half of a fermion. And these objects then are like an orbital, the half orbitals, which is a very, very strange concept. But it's at the heart of one attempt to build a quantum computer, the one by Microsoft. And I guess I'm running out of time, so this is just showing this scheme of braiding these things around each other to process the information. Microsoft not using the quantum Hall effect, it turned out afterwards that we could find other systems to have these Majorana zero modes. In particular, if I couple a one-dimensional system with strong spin orbit coupling to a superconductor, we could formally write an electron creation. We can formally take the electron apart into real and imaginary parts and a phase which represents its charge. So if the superconductor kind of removes the charge from the electron, it all moves to the surface of the superconductor. So only the kind of fermion number is left, and this can be split into real and imaginary parts formally. So we can rewrite the Hamiltonian of this system in terms of Majorana modes. And the interesting thing is that this is completely formal, mathematical, as long as everything is local. Entanglement is only useful if it's on a scale larger than atomic scale, right? Entanglement is everywhere around us. The chemical bond is a maximally entangled thing. Entanglement becomes mysterious and strange in its properties when you can form entangled systems which are far away from each other. And in this case here, you can formally write the electron operator in terms of real and imaginary parts and split them when they couple it to a superconductor. But the superconductor makes them recouple in a different way, exactly like the spin chain. So you make them this way, but the superconductor kind of make them recombine here, and you get left with this half orbital at the either end of the so-called Kitaev chain. So it's a generalization of the simple original meme in the spin chain. So the Microsoft have, the year, there's been a lot of hype about this stuff because it looks great on paper. It's kind of like fusion, right? Fusion is definitely on paper the solution to all our energy problems, but there's always been little problems in getting it to produce a practical fusion. Something similar is happening here, I suppose. 2017 was predicted to be the year when braiding and quantum information was going to be established, but it came and went, and there were these announcements in Delft in the Netherlands, which turned out to be incorrect, and it faded. But Microsoft have kept working on it. More recently, they published, but they put out a whole lot of YouTube videos about their new Majorana 1 architecture, but it's still got problems. The Majorana 1 architecture is a kind of H. It's got these superconducting stuff here, wires, and it's got these 4 Majorana 0 modes at each point on the H, and you can couple them either this way or couple them that way. I guess you can't, there's no coupling across the third direction. But so far, the jury's out to what extent this is actually not really a working qubit yet, because part of the reason is the exponential decay length is too long. They're not well separated enough that the size of the H is not big, is not sufficiently big compared to the exponential decay length. So anyway, so this is this is part of the excitement people have in this area. Oops. Not moving. Okay. It's only one of the approaches to quantum computing. The more regular ones, which are building so-called NICs, noisy intermediate scale qubits, have been progressing pretty well, but there's always an exponential barrier to doing that. We'll find out to what extent quantum computing becomes, if it ever does, it becomes a kind of practical thing, but it's looking interesting, at least from the point of view of these other approaches. So for scaling, the topological thing is great on paper. So let's go the other way. It's a kind of beautiful dream. I mean, I'm not going to tell you to invest your pension money in topological quantum computing, because physicists always they love their kind of theory, but whether it's practical or not is a separate question for technologists. But I think it's the fact that material science has managed to build all the kind of interesting toy models we've been coming up with makes me confident that we will eventually see braiding and see if it actually works for things. And I guess that's my end of my talk. Thank you.
Okay, so thank you very much, Professor Haldane. We have time for one quick question. If anyone wants to. Nope. Okay, well, actually, I have a question a bit general, and it's, which do you think is going to be like the next big discovery or big announcement in quantum physics?
Oh, I don't know, actually. So where things, I mean, this would be great if it actually is achieved to actually put some information into one of these systems, do something with it and get it out again. I think whether that gets the Nobel Prize is going to be, if it happens, is going to be problematical because there's so many people who have a claim on this theoretically, and both presumably the experimentalists who make it happen. But I don't know. But the quantum technology, I think, has got what's actually happening as well as trying to make the qubits for the quantum information processing, the qubits also, one aspect of the qubits is the fact that they do interact with the environment, right? So there's going to be a whole new generation of sensors for very high precision measurements, like nitrogen vacancies in diamond can be used to get extremely exquisitely fine measurements of the magnetic field and trace the, every point on the Earth has a kind of fingerprint coming from the microstructure of the magnetic field, which can be used to identify where you are. So there's proposals to have a backup to GPS. I guess you'll still need to send your fingerprint back to an AI computer to tell you exactly which part of the Earth it matches. But and so there's actually a lot of, I think quantum technologies, especially in the sensor thing, have an immediate aspect in the next couple of years. There's going to be a lot of things, and presumably maybe, I mean, certainly in gravitational waves, you're using quantum technology to be able to measure these things. I'm not sure with telescopes and things, but I'm sure that precision measurements have a great impact on future telescopes too.
Okay, so
it's a very silly question coming from left field, but I was wondering, because all these very interesting effects are basically the result of the wave function interaction when you have many body systems.
Yeah.
But I'm just thinking out loud, because you're mentioning that these electron states have this behavior. Could this be ported, let's say, into fundamental aspects, basically the property of the electron itself? Or would you say simply it's because it's a collective phenomenon, it's happening this way because you mix a collective system with quantum mechanics?
Yeah, these things have all come from this collective aspect of underlying the topological order appearing as a kind of generalization of long-range order in systems. For the individual, yeah, I mean, I guess the theta term is supposedly there for the axions in the Lagrangian of beyond the standard model or whatever. But yeah, so, or the electric dipole moment of the electron or something. Yeah, I don't know to what extent, unless the structure of space-time itself has some stoppage. I mean, some people go into these kind of speculations.
Very interesting to see, because
Yeah.
after many decades, fundamental physics has not advanced and string theory has failed. So I think it's
Yeah.
interesting to see
So I mean, a lot of this stuff actually looks, I mean, when people wanted to do calculations in elementary particles, they moved on to lattice QCD, right? And then you can have all kinds of, Z2 theories on lattices and things. So in some sense, a lot of what's happening in the condensed matter world is like lattice QCD, except that it's a real lattice. It's not like it's a real 3 plus 1 dimension, three dimensions plus time. But now with quantum circuit theory, it's becoming, for doing abstract measurements, it's actually being discretized. But the evolution of time is being discretized by a sequence of gates, right? You have a set of thing, and you time evolve the Hamiltonian or evolve things by implementing discrete time intervals with gates. So actually, I mean, this stuff is a bit like, but now when you liberate it from the need to kind of fit in with kind of regular Lorentz invariant space-time, there's a lot more kind of discrete structures which are being discovered and have all of these interesting topological properties. So in many ways, lattice QCD type stuff is like simple versions of some of this stuff here. And with this thing of quantum circuits, where you actually evolve your system, you simulate the system in qubits, and then you evolve it with gates, that actually is exactly like the moving to from 3 plus 1 Lorentz to 4 plus 0 Euclidean. Yeah.
okay, so let's thank again Professor Haldane for the talk, please. And thank you for coming. Just a reminder that we will have a coffee right now in the cafeteria, and the students, please come down so we can check your attendance. And please, if you can leave the aula, because there's another seminar at 12 o'clock. Thank you.